My name is Phil Lombardi, and I'm an engineer at Datawire IO, and today I'm going to present on Borg-like resilience for your microservices. Just a little bit of information. So, as I said, I'm Phil Lombardi, working on Datawire IO. Basically, Datawire IO is building a microservices development kit to enable developers to build resilient microservice applications quickly and efficiently. You can check us out either during the talk, after the talk, but you can go to app.datawire.io. I won't be offended if you play with our product. So I think it helps basically to start any of this conversation about microservices by giving a little bit of information about what a microservice is. It's a big buzzword these days. And so you often hear people kind of describe what a microservice is. And they'll give you definitions about the attributes of a microservice. It's that it's a small, self-contained, narrow in scope, has bounded contexts. It's independent, loosely coupled. And yeah, these are all properties of really good microservices, well-designed microservices. But when they've given you this definition, they actually haven't told you what a microservice is. So to just make it a little bit easier for the context of this presentation, I'm going to clarify and say that a simple definition for microservices is that it's a unit of business logic. And so when I say it is a unit of business logic, I'm talking about basically it's a thing that takes an email and sends it to somebody. It's something that adds a contact to a database, anything that's really basic and by itself not particularly useful. But when people talk about microservices, they're not really talking about these independent little pieces of code that do things. They're talking about an application. And so what occurs is people build an application from microservices. And it's a distributed composition of business logic via services. And so basically, when you start doing this, you end up with a situation where you get a lot of really good benefits by doing it, but you also take some trade-offs. Microservices, when you start building them this way, the great thing about them is that you have a good insight into what the individual components do. You can reason easily about what a service that sends an email does. You can reason easily about a service that adds or removes a contact from a database. So it makes it really easy to add new features and kind of build your application. But you run into some problems. One, it's a pain to deploy these services. If you thought deploying a monolith was at all difficult, then you are in for a whole new world of pain with deploying a set of microservices. There are many of them. They have to be glued together. They have dependencies. They may be circular dependencies. They're also more difficult to operate. If you thought that your monolith was difficult with just server failures or network partitions, network failures, storage array failures, take that and distribute it over thousands of little pieces of code that are now running. But you can actually do pretty awesome things with them. And people have been using them pretty successfully. Some of these companies, Halo, Netflix, Twitter, I'm sure every one of you have used them every day. They've built massive, massive applications by composing this functionality together. What they end up calling these things really is a Death Star topology. And I promise this is actually going to be back to Star Trek and not Star Wars, but that's what the parlance is for these things. But Death Stars are terrible. They actually are single points of failure until that guy from the desert basically decides he's going to put a torpedo down the vent shaft. They don't fail in reality like that. So, when was the last time you can think of a Netflix going down? Twitter, Uber, Yelp. They fail, sometimes for local reasons. Your network connection doesn't work. They have a much larger problem. For example, AWS or Google Compute Engine goes down. That can be catastrophic in ways that is almost impossible to engineer around. But they don't fail because of, say, bugs in their code. And they don't usually fail because of a server crashing. So while the Death Star itself was brittle and it has single point of failure, these Death Star topologies are nothing like an actual Death Star. They're not brittle. These systems are very, very resilient. They survive basically a whole class of issues that we run into as engineers. Hardware, network issues, software bugs, security exploits. And yet, every day, engineers are working on these systems. They find and fix these issues without actually having to stop these systems, add new features to the product to continue to deliver business value, and alter the system multiple times a day, causing the topology to shift and change constantly. There's no way they could actually stop these things, basically pull them down, deploy these changes. There's just too many people working on them, too many teams. So what we actually have are these guys, the Borg. And these systems are a lot more like the Borg than, say, a Death Star. And just to kind of recap for those who are not really Star Trek fans, the Borg, they were a collective hive of drones, which we can kind of think of as our business logic in the system. They're loosely controlled by the queen, which might be an orchestration system for infrastructure, discovery system. But basically, they were nearly impossible to stop. They routinely took on numerous adversaries. Those in our world would be bugs and security threats. They also often, basically assimilated, everything that was around them. There was basically forced evolution around technology and societies they ran into, so they could do that. The other really cool part about the Borg was they continued to make progress no matter what. Even when they were disconnected from basically the queen or the rest of the drones, they just continued to know what to do. They did this by this thing called secondary objectives, which that kind of resiliency might be in our world kind of mapped to being able to continue to work despite hardware failures or network outages. So how did these companies actually become Borg-like? Well, they needed to build a new architecture. And the new architecture made them extremely resilient to the two classes of things that we actually run into on a daily basis: infrastructure failures and software bugs. So when we think about failure types as engineers, there's these things that we always engineer for. We always know, networks fail, servers fail, storage fails, and resource limits. Especially this is, the case if you're running on, say, AWS, where you're going to run into quotas around the performance. You might be throttled for doing things you're not supposed to do, or for, abusing their system. This also applies for any other PaaS or IaaS out there. But then there's the stuff that we think we're engineering for. There's those integration bugs and those functional bugs, and often we just don't put enough actual thought around that, so we really aren't engineering for that. In a microservices architecture, basically integration bugs, they're going to be your new worst enemy. You're not going to be able to stop the world and basically get a whole system up and running at any point in time in one of these architectures. You just can't. They're changing way too often underneath you. So even if you could stop, say, a Netflix and bring up the 500 services at point t and 0 in time, and then test your new service, by the time you got it tested, someone's already probably built another service and is using that, or has deployed a new version. Further, there's really no compiler that you have in a classic monolith, where it's going to check to see that, make sure that your method calls are correct, or that your data types that are moving between the method calls are correct. So you don't have type safety. And I want to say that's completely true. It's not totally true, because people use basically IDLs, which give you some strong contracts between services. But you can also think of how people abuse those contracts. So for example, if you're writing a service and you have a client service that starts consuming you, and he decides that he's going to put in a busy loop a request to you 1,000 times a second, and there's no way you can prevent that without having some kind of strong integration testing or just resilience in general. So basically, you have to learn that integration bugs are a way of life in a microservices architecture. And that's what these guys basically learned. So it was born from a need to be resilient to these things. They already had engineers working on stuff. And you can't make engineers just magically write bug-free code. We all write code that is probably riddled with bugs at times. It's just a way of our lives. So they need to basically build the architecture itself to be able to handle bugs that were going to be produced by their engineers. So, kind of just to recap, our traditional architecture tends to look like this. We have a client service. This is not necessarily a web browser. This may just be another service in the back end. It's talking to DNS, and that DNS will resolve a load balancer name for it through a CNAME or an AA record. And then that load balancer will then route traffic that's forwarded to it over to a bunch of back-end servers. And so when I say below the routing table is relatively static, what I'm saying is that the DNS names don't usually change too often for the load balancers. And when I say the routing policy is global, what I'm really saying is that the client doesn't get to select which server it talks to. And you'll find out this is a really big difference from the traditional architecture to the newer architecture I'm going to show in a moment. So your load balancer is designed to protect against infrastructure failures first and foremost. Basically, when those servers fail for hardware reasons, the load balancer fails its health checks. When the network fails, the load balancer fails the health checks as well, and clients will stop going there. But in 2016, our biggest issue with these servers is not actually writing them so that they're basically avoiding infrastructure bugs. It's that lovely integration bug as you roll out 1.1 of your new service. So think about this. Your client is coded to need JSON data, and your engineers who are building the application for 1.1 start basically, still sending JSON data, but they remove a field that's critical to your application. And your client now is basically vomiting all over the place with exceptions and stack traces. Your load balancer is pretty happy about this. It's still going to be chugging along. It's going to see a 200 response from the server, continue to respond, and send the information to the clients as it's requested. but your application is failing miserably. So some smart folks basically figured out a better way, and it's actually called the smart endpoints architecture. And we call it the smart endpoints architecture for a reason. Each node is smart because each node knows about how to communicate with every other node without a load balancer. The intelligence of a load balancer is moved into basically the client-side application. Similarly, when an integration back, we can blacklist the misbehaving service node and still use the other set of nodes. So no longer do you have to rely on the load balancer itself to be the thing that decides whether the remote service is working. The client has basically the ability to do that. The end result of this is a collective mesh of intelligent intercommuting service nodes, basically the equivalency of the Borg collective. So here is what the smart endpoints architecture really looks like. As you can see, we've removed the global load balancer. We've basically moved it over to the client. This could be, whether it could be like an nginx that runs on the client side, it could be a custom code that runs here, but the idea is you move it onto the client side. Then instead of having a DNS server, you're going to have a discovery server. And basically what occurs here is the servers that are running in your backend are going to be continually publishing their basically heartbeat status to this discovery system. The discovery thing then basically acts as a broker. It pushes the client information over, it pushes the remote service information over to the clients, which is really important because what's occurring here is that those backend servers, because they have to talk to discovery, are basically acting, that discovery system is, the best way to say this is it's preventing those infrastructure issues we had before. If the heartbeats don't get delivered to discovery, then discovery believes that the servers are gone and will eventually evict the records itself of those backend servers from there and then forward that expiration notice to the clients. Now, you may be thinking, but doesn't that just make discovery itself a single point of failure? And not really. And I'm going to answer that question basically on the sense that if discovery goes down, the clients in this system are actually maintaining the local routing tables themselves. So if discovery goes down, the only actual outcome here is that new services, as they come up, cannot be added into this system. But the clients can still talk to each individual server in the background. And when it gets finally recovered, when discovery comes back, it starts basically blasting the known new state of the world back. So it's still resilient in that sense. Now, think about the world where we had the software integration bug that occurred earlier. Your 1.1 goes out and your client is talking to it. But the beautiful part about this, instead of failing before catastrophically, where 25% of your traffic could be going to that bad node, or 33% of that traffic could be going there as you roll out more and more, only a small percentage of traffic goes there. Your client will eventually, you will basically get a failure signal from that server based on a stack trace being blown or something when it gets back the request as a response, and it will blacklist the node. It'll be completely taken out of its local routing table. And so no longer is traffic just being hemorrhaged over to a bad node completely. And what's really, really cool about this is each one of these clients is running its own concept of what works in this system. So think about this. If you have a client that's set up so that it is basically requiring some field that's in that data that comes back from the new 1.1 service or the 1.0 service, but there's another client in your system that does something totally different that doesn't actually require that field, only one of them will fail. And so the other ones continue to work on resiliently. So what is actually powering this technology? And it's something that we're all pretty familiar with, and it's really pretty old. It's a circuit breaker, just moved from the physical world into the digital world. Basically, this entire thing works on the idea of circuit breakers. And nodes independently track its usage of these remote services, and when they encounter failure due to software or infrastructure, then the remote service is basically blacklisted. And it can be blacklisted, either temporarily, for reasons, for example, temporary blacklist might occur because you have a network failure or a network partition. Those are things that can be recovered. But it might also be removed permanently. For example, in that integration set issue, you're never going to fix the issue where the service 1.1 is returning invalid JSON. You're going to have to wait until someone rolls out a 1.2 and fixes it. But you don't. Basically, the idea is that it also doesn't affect the other nodes. Those nodes all have their own concept of what works. So, smart endpoints in a nutshell. There's really two very big important things here. It's that each service maintains its own record of addresses in the environment. A service can then in theory talk to any other service. And the circuit breakers prevent catastrophic failures by blacklisting misbehaving nodes. Blacklisting is done, once again, on a per node basis. And really what we're getting out of this thing here is a huge thing. Smart endpoints allow us to do quick integration testing. Because we don't have to worry about catastrophic cascade failures, by blacklisting the misbehaving node and talk to a known working nodes, we can start rolling out new features really quickly and basically not worry about them causing destruction of the entire production environment. Similarly, smart endpoints make the integration bugs far less dangerous and therefore enable faster development cycles. If you have faster development cycles, you can try new things more quickly. Your business guys can come to you with ideas and say, we want to try this. Your engineers can start bringing new technologies into the stack, and they can start changing things in any way they really want to. And they can do it with confidence. They can do confidence that they're not going to be waking up operations in the middle of the night, or they're not going to be getting their manager yelled at by the business guys going, why is this thing taking out the critical systems? And you still get the benefit that it's preventing the classic infrastructure issues that we already have to deal with using basically centralized load balancers. Do you see where this is going? So back to the Borg-like architecture. If smart endpoints prevent catastrophic software failure, then the following things become true. Change becomes a way of life. Modifying the system with new services becomes something developers, managers, operations all feel comfortable with. You have to understand that basically the system underneath you is changing at all points in time. It is a living system. So we start treating software more like an organism and less like this concrete building that we're constructing. Change means new technologies can be integrated. You can basically build best-of-breed stuff. You can also fix your bugs that you have in production. You can fix security issues. And you can do it without basically worrying that it's going to end the world. If it does, one service falls down, you go off and you remove that service, or you just roll out a new version and tell everyone to talk to the latest version. The end result is basically that we're going to end up with an application that is in a continual state of improvement, which is everything that we always strive for, both as developers, whether you be a developer, whether you be in operations, whether you be a DevOps. We're always trying to make things better. So if you want to learn more, you can contact me. That's my email address. I'm happy to talk. I respond to every email. You can also reach out to me on Twitter. We're hiring at Datawire.io. I would love to find anyone who's a Java, Python, Go, or Kubernetes developer here today and talk to them a little bit. We're out in Boston, but we can potentially talk about remote work. And also, like everything I talked about we're working on is open source, so you can try it out. No strings attached. You can go there. The app that we show on the URL I put up earlier, app.datawire.io, that is closed source, but it's just some JavaScript. So really, it's not closed source. And that's it. Thank you. Questions?
Some of the things with the star approach, how do you handle things like circular dependencies and contracts with services talking to each other?
Yeah, so circular dependencies is just icky. You can actually set it up so your circuit breakers can look to see the dependency chain. So what I didn't talk about here was things like you can start putting context about the request chain in there, and when a service finally gets back to saying, oh, I'm actually handling myself, and you can basically stop it. And it fails the entire thing, and then that would cause a failure that goes back to the client, and it would end. You really want to avoid doing circular dependencies if you can, but it's actually unavoidable. So you have to figure out how to kind of work around them. I've also heard people doing basically breaking circular dependencies using things like event sourcing models. I have not actually used that technique, but I was at another conference, DockerCon in June, where someone basically was like, I solved the circular dependency issue by putting it in an event source queue, and that was it. So, anyone else? So for example, you could do two things. The question was the question was basically, I understand how the circuit breaker piece works, but how are you actually getting the load balancer to work that's on the client side? So think about it this way: you could embed nginx locally to the service, then route all the traffic through nginx localhost and let it handle that. You could also, that's one technique. Another code technique is you can write a lot of custom code around that. So if your service discovery system is actually a little bit intelligent, you can put all kinds of statistics and information in there, and then basically your code paths can intelligently react to that. So I wasn't really giving a super great, this is exactly how you do it. It's more of an abstract pattern for how you would make this work. Anyone else? Right there?
It seems like API versioning could help us with this problem in a more, I don't know, well-structured or easily identifiable way. Have you thought about that, or what?
API versioning is in the sense of every API that gets published out into your system has a version with it. So so one thing I didn't mention about discovery is you're usually publishing both a service name plus a version associated with it. So then you can have your discovery system. So when you actually request things, when you're publishing the records back to the local client and it's looking at its local routing table, you can do queries against that. So you can say, I only want to use any major version, or I can use any major minor version. Especially if you're following like a semver pattern, you can get really specific. Even further, like the cool part about this, and I didn't talk about this at all because it would just take too much time, is you can start to do things like override requests. So say you want to test a specific version of a service that you've deployed out there, like v1.13.60.alpha, and you can actually feed away. You could write your code to feed in that information, and then have basically the local routing table get you the right server for that, and then send the request just to that server. So that's one technique. Anyone else? Cool.